This is CPM Calculus Chapter 4, number 50. So here we're asked if n is a positive integer, so n has to be greater than 0. So it starts at 1 because it's an integer. It has to be 1 through any big number, goes 1 to infinity. Write an integral to represent this. Okay? So we want to represent this as an integral. So what we can quickly recall is that the integral from a to b of f of x dx is the same thing as taking the limit as n approaches infinity of our Riemann sum starting at any variable, let's say I is 0 to n minus 1 of the width times the height starting at a plus the width times our variable I, right? And that's equal to the area between our function and bounded by a and b. Okay, remember this is the exact area, not approximate, because we're taking the limit as n goes to infinity. So let's look at this. The first thing I would do is just kind of see, can I simplify this at all? And yes, we can. We can distribute this to every term here, right? And this is going to be 1 over n times 1 over n plus 1 over n times 1 over 2 over n plus plus 1 over n times 1 over n, right? This is just distributing the 1 over n here inside these brackets, okay? So then we have the limit as n goes to infinity. And now we can go ahead and simplify this. This is over here in the numerator, we have 1, right? In the denominator, we have n, so I can put n over 1 times 1 over n. These are going to cancel out, and it's just going to become 1, right? Or 1 over 1. Plus, here we have n over 1 again. So when we multiply the numerator. So 1 times 1 is 1. In the denominator, the n's cancel out again. So we have 1 over 2. Plus, the next term is going to be 1 over 3, 1 over 4, plus the last term, right? This one we know is just 1, so this is equal to 1 over n. So this makes the problem a little bit more simplified, right? Because we just have this as our series. And we could write this in sigma notation, right? We could say, well, this is the same thing as, I don't know, our variable I starting at 0 and going to n, right? This is just 1 over I plus 1, right? Because we start at 0 and we're stopping at, excuse me, not n, but n minus 1, right? When I is 0, we get 1 on the outside, right? We get 0 plus 1. When I is 1, we get 1 plus 1 is 2. Then when I is 2, we get 2 plus 1 is 3, all the way through n. And that's equal to the limit, we still have the limit as n approaches infinity out here. Okay? Remember this up here, right? Because this shows us that, well, all we have then, this is equal to the integral, right? And where are we starting? Well, we don't have, we don't have this a, so a must equal to 0, right? A must be 0. Where are we stopping? I don't know yet, so let's just leave that blank. And our function is going to be 1 over x, for example, right? dx, because this is in the form of 1 over x. So where are we stopping, right? What is this stopping point? Well, remember that this is a to b, right? And so we want b to be where we're stopping. Remember that. Okay, I said that already. Well, delta x, we know, is equal to b minus a over n, right? And again, this right here is the delta x that we're adding in each time to get to multiply the base of every rectangle times the height, times the height, times the height, right? We're getting the areas. We're also adding delta x each time. If we add 1 over n to 1 over n, we get 2 over n. If we add 1 over n again, we get 3 over n in the denominator, all the way until we get n over n. So we know delta x is equal to 1 over n, right? So on the side here, I'm going to say delta x is 1 over n, and that's b minus a over n is equal to 1 over n. And if I know a is our starting point is 0, so I know b minus 0 over n is equal to 1 over n. I can multiply both sides by n to get rid of those n's, and I know b minus 0 is equal to 1, so b has to be 1. So my stopping index, or boundary, is 1. Okay? So I can go ahead and box this now, because this is the integral representation of this given Riemann sum, or sequence of numbers. Okay? Alright, so that ends CPM Calculus Chapter 4, number 50.